something is wrong with the sky. Not wrong in the way astronomers expected, not wrong in the way that produces polite concern in journal papers and quiet revisions to existing models. Wrong in the way that makes scientists go silent. Wrong in the way that forces entire research teams to stop, stare, and recalculate everything they thought they understood. Because the Vera Rubin Observatory has just released a new wave of images, and what they contain is not simply beautiful, not simply historic. It is, by any honest measure, terrifying. Not terrifying because something is coming, not terrifying because a threat has been detected in the traditional sense. Terrifying because of what these images reveal about the scale, the violence, the hidden chaos embedded in a universe we believed we had begun to understand. In a matter of weeks, Rubin has gone from delivering its first breathtaking mosaic of the Virgo cluster to capturing images that are shaking the foundations of cosmology, planetary defense, and our most basic assumptions about the structure of reality itself. The sky is not what we thought it was. It is darker, more crowded, more violent, and more dynamic than any model we built predicted. And Rubin just proved it. What the telescope captured in its latest observation run isn't a single discovery. It is a cascade of them, arriving faster than the scientific community can process, each one more disorienting than the last. A population of previously invisible near-Earth asteroids so dense that planetary defense researchers are quietly revising their risk assessments. A network of dark matter filaments so precisely mapped that it contradicts several leading cosmological simulations. A cluster of galaxies caught in the act of collision so massive and so energetic that the shockwave alone spans 10 million light-years. And buried within the data, something that no one predicted at all, something that has no clean classification, no tidy explanation, and no precedent in the history of observational astronomy. The universe just showed us something new, and it did not ease us into it. To understand why these latest images hit with such force, you have to understand what Rubin has become in just a matter of months. When first light images were released in mid-2025, astronomers praised their scale and depth. But those early images were calibration runs, test frames, warm-up scans of familiar regions. What Rubin is doing now is its actual mission. The Legacy Survey of Space and Time, known as LSST, the most ambitious systematic sky survey ever attempted. Every 3 nights, the full southern sky is scanned in 6 different wavelength bands. Every 15 seconds, a new 3.2 billion pixel exposure is captured, processed, and fed into a pipeline that identifies changes, flags anomalies, and broadcasts alerts to astronomers around the world in under 60 seconds. Rubin is no longer warming up. It is running at full speed. And the data it is producing is unlike anything the scientific world has seen before. The first shock came from the asteroid detections. In its initial test run, Rubin identified over 2,000 new asteroids in 10 hours, including 7 near-Earth objects. Scientists celebrated that number. They called it a proof of concept. But now, with the LSST running in earnest, the detections are not scaling linearly. They are exploding. Rubin is discovering near-Earth asteroids at a rate that has forced the International Astronomical Union's Minor Planet Center to upgrade its processing infrastructure just to keep up. Entire categories of small, fast, dark asteroids, the kind that absorb radar rather than reflect it, the kind that previous surveys missed entirely, are now emerging in enormous numbers from the data. These are not distant, comfortable objects drifting in the outer belt. Many of them have orbital trajectories that bring them uncomfortably close to Earth's path. Not on collision courses. Not yet. But their sheer abundance is revealing a solar system that is measurably more hazardous than our models suggested. The sky we thought was familiar turns out to have been hiding a population of objects that were always there, patient and invisible, waiting for a telescope powerful enough to find them. But the asteroid detections, as alarming as they are, pale against what Rubin's deep imaging has done to our understanding of dark matter. For decades, scientists have mapped dark matter through gravitational lensing, the way massive invisible structures bend and distort the light of objects behind them. It's an indirect technique, painstaking and narrow in scope, limited by the field of view of the telescopes doing the work. Rubin removes that limitation entirely. Its wide-field imaging covers so much sky so rapidly that it is building a gravitational lensing map of the cosmos at a scale that was previously inconceivable. And what that map is showing is disturbing in a very specific way. The filaments of dark matter connecting galaxy clusters, the invisible skeleton of the cosmic web, do not follow the distribution that our best simulations predicted. The structures are there. The web is real, but its density, its texture, and its geometry in certain regions deviate from the lambda CDM model, the standard model of cosmology, by margins too significant to dismiss as noise. This is not a minor discrepancy. This is a structural mismatch between our most successful cosmological framework and the actual universe as Rubin sees it. And it is generating serious, urgent conversations about whether something fundamental in our understanding of dark matter physics is incomplete or simply wrong. Then came the galaxy collision. Captured during a routine scan of the southern sky, Rubin's latest wide-field images revealed a system of galaxy clusters in the process of merging, not in the quiet, slow gravitational dance that most mergers resemble, but in a high-velocity, high-energy impact that is releasing kinetic energy on a scale that dwarfs the most extreme events previously catalogued. The shock wave moving through the hot intracluster gas, visible in X-ray, and now mapped in extraordinary spatial detail by Rubin's optical data, stretches across 10 million light-years and is still propagating outward. The collision itself happened roughly 2 billion years ago. What Rubin is seeing is the aftermath still rippling through the universe, still reshaping the environment of thousands of galaxies caught in its path. Galaxies that once had orderly spiral structures are showing signs of compression, star formation triggered by the pressure wave, and in some cases the complete disruption of their stellar disk. The collision is not just a spectacle. It is a laboratory, a natural experiment showing how the largest structures in the universe evolve through violence, and how the shock waves of cosmic impacts can alter the fate of billions of star systems at once. What makes Rubin's images of this collision truly unsettling is the resolution at which we can now see the aftermath of cosmic violence. Previous surveys caught hints of these structures, broad strokes of distorted light that suggested something enormous had happened. But Rubin resolves them into detail, individual galaxies caught in the shock wave. Tidal streams of stars pulled from their host galaxies and scattered across millions of light-years. Faint arcs of gravitationally lensed background light bending around the immense dark matter concentrations in the collision zone. These are not abstractions. These are real structures, resolved, catalogued, and now demanding explanations that our existing physics must either provide or admit it cannot. The universe is doing things at scales and in ways that continue to outrun our ability to fully model them. And then there is the anomaly. Buried in one of Rubin's wide-field scans of an otherwise unremarkable region of the southern sky, the automated detection pipeline flagged something that did not fit any known classification. It is a faint, extended object, roughly the size of a dwarf galaxy in angular scale, emitting light in a pattern inconsistent with stars, nebulae, or any catalogued galaxy type. It does not pulse like a pulsar wind nebula. It does not stretch like a tidal stream. It does not cluster like a globular association. It is diffuse, roughly elliptical, and it appears in multiple filter bands in a way that suggests it is not an imaging artifact. It is real. It is physically there, and as of this moment, no one has a definitive explanation for what it is. Theories being circulated include a fossil galaxy stripped of nearly all its stars by ancient tidal forces, a supercluster halo imaged at an unprecedented surface brightness depth, or an entirely new class of diffuse stellar structure that Rubin's depth has made visible for the first time. Whatever it is a reminder that the universe has not finished surprising us, that for all our models, all our surveys, all our accumulated centuries of observation, there are still things out there that we simply did not know to look for, because we never had an instrument powerful enough to show them to us. This is the nature of what Rubin is doing. It is not finding things we expected to find in places we expected to find them. It is revealing a universe that is structurally richer, dynamically more violent, and categorically stranger than the one described in the textbooks written before it opened its eye. Every scan adds not just data, but complexity. Not just answers, but new, deeper questions. Rubin is the first telescope in human history capable of seeing the sky as a system, rather than a collection of individual objects. And when you see the whole system at once, at the depth Rubin reaches, the picture that emerges is not comforting. It is vast, it is chaotic, it is ancient beyond comprehension, and it operates by rules that we have only partially decoded. The scale of what is coming is almost incomprehensible. By the end of its 10-year survey, Rubin will have cataloged 20 billion galaxies. It will have detected tens of millions of asteroids and tracked the orbital evolution of thousands of near-Earth objects. It will have mapped the three-dimensional distribution of dark matter across a volume of space spanning billions of light years. It will have recorded the light curves of millions of supernovae, variable stars, and transient events that no previous observatory captured. It will have built the most detailed, most dynamic, most complete portrait of the observable universe ever assembled. 500 petabytes of data, a number so large it resists intuition, encoding a decade-long time-lapse of the cosmos at full resolution. And embedded somewhere in that archive, scientists are almost certain, are discoveries so fundamental that they will require new physics to explain. Not revisions to existing equations, new physics, new frameworks, new ways of thinking about space, time, matter, and energy that do not yet exist, but will be forced into existence by the evidence Rubin is collecting right now. That is the real weight of these new images. They are not just photographs of distant objects. They are the first dispatches from a new era of human knowledge, arriving faster than we can absorb them, carrying information that is already forcing science to evolve. The universe has been hiding things from us, not maliciously, not mysteriously, simply because we lack the vision to see them. Rubin has given us that vision, and what we see, now that we finally have it, is a cosmos that is grander, stranger, more violent, and more magnificent than anything we imagined when we first turned our eyes to the night sky thousands of years ago. We are not at the end of understanding the universe. We are not even at the beginning of understanding it. We are at the moment when the lights come on for the first time, and we are just beginning to make out the shape of the room. The room is enormous. The room is extraordinary, and some of what is in it does not yet have a name. So here is the question that should keep every one of us awake tonight. If this is what Rubin finds in its first months of operation, in its first fractions of a % of the total data it will collect, what is waiting for us in the other 99.9%? What structures are out there that no model predicted? What objects exist that no classification covers? What cosmic events are unfolding right now, at this very second, in regions of sky that Rubin's lens hasn't yet touched but will? The universe is not running out of secrets. It is revealing them faster than we can record our astonishment. And we are only at the beginning. If that excites you, if that unsettles you, if that makes you want to be there for every discovery, every anomaly, every moment when science is forced to rewrite itself because reality turned out to be more extraordinary than anyone dared to predict, then you already know what to do. Stay with us. Because whatever Rubin sees next, you will not want to find out about it alone.